So today we are going to focus on the general idea of mean field theory. And this is actually the simplest way to address interactions, which in some way it is equivalent to first order perturbation theory, but we'll see today one example that we started discussing last week, and then a less trivial example where mean field theory is an approximation that allows you to treat in a simple manner many-body problem with two-body interactions, simplifying them, but with the mean field idea, you can make a guess on the ground state, on the corrected ground state, that can be verified self-consistently, and we'll see it today. So, or we'll start discussing it today. I will start with the example that we already discussed last week at the end of the lecture, and this is the Hartree-Fock approximation. Okay, so, I'm focusing on fermions throughout the lecture, but of course, everything can be generalized to bosons, except there is this zeta that takes the value +1 when you are bosons and -1 for fermions. So I'm just writing it here for a reminder. Okay. So what is the idea? Let me write a general interaction term, interaction operator, and it has the following form. I'm summing over 4 indices that correspond to the quantum numbers of the single particle problem. And let me just write on the side that the problem we generally want to solve is there is some single body Hamiltonian that we know how to solve, and we can find the basis that diagonalizes it. This is something that you can write as in the diagonal form. Lambda is the quantum number, and these are the creation and annihilation operators plus interaction, and the interaction is two-body. So it has the following form. There's a matrix element. And then we have A mu prime dagger, A lambda prime, A lambda. Okay, so this is it, and now the mean field idea is the following. We don't like to work with two-body operators because we don't know how to solve generally the Schrödinger equation when both one body and two body are together. So what we're going to do is to replace one of each pair of operators, of each two pairs of operators by an expectation value. This is going to be a number, and then we're going to get an effective single body Hamiltonian that adding it to H naught, we can easily solve, okay? Maybe it will even be already diagonal in the basis. If it's not, we know how to diagonalize matrices, especially if they are 2 by 2. Okay? But numerically we can, of course, do even better, but in any case it will be already a step forward. Now, what does it mean to replace an operator by its expectation value? Let me generally explain what I mean. So an operator, you can always write in the following way, and this is of course trivial. Okay. Right, I just added and subtracted something. And when you replace it by an expectation value, what are you missing? You are neglecting this deviation. Okay? Now, this deviation is an operator, it's not a number, but in some sense, if it's small, of course, by itself you cannot tell whether it's large or small because it's an operator, it doesn't have a value. But when you plug it into an expectation value or a matrix element, you can quantify it, and if it turns out that it is small and you neglect it, you can replace the operator by its expectation value. Okay? Yeah?
It's normal ordering with this side.
This is normal ordered, okay? It's normal ordered with respect to the vacuum, the real vacuum, but here what I wrote is completely general. Okay? Of course, if this, now I also have to define when I'm writing expectation value, it's also not well defined. Okay? I'm not telling you whether it's the vacuum or not. So what is this? It's an expectation value in some state, right? Now, if I choose this state to be a ground state, I'm also assuming some bias on the ground state. So when I say expectation value, I have to tell you which state I'm calculating it in. Okay? And that's very important. Okay? All right. So what do we do in the Hartree-Fock approximation? We basically take this combination of 4 operators. And we are replacing it, color, we are replacing it by an expansion over contributions, each of which is replacing only one pair of operators by expectation value and leaves the other intact, and this way you get a single body Hamiltonian. Now, by doing this procedure carefully, actually, you get something that also acquires some constant, right? Because you can think, the way to do it carefully, I don't want to spend time on the algebra, I think you will do it in the tutorial, but I'm basically using this, writing it for each of the operators and expanding it. Okay? And in the end, you'll get a constant plus something. The constant is usually not important unless you really want to know what is the value of the ground state energy or something like that. Okay? What is important is what is the remaining form of the operator. And basically what I'm saying is that I'm replacing this by some constant plus the following expression, and quite generally, let me first write it generally, and then we'll see which part is actually 0. So I'm writing an expansion of terms where each time I take one pair and replace it by its expectation value. So the first option is to put the expectation value on this. Okay. Or it's a Hermitian conjugate, basically, which is okay. And then the second, there is the following term. I'll write it like this. Which is coming from, so these terms come from putting contractors on either this or this, and this term comes from putting the contractors between two adjacent A dagger A, and either this or this, it doesn't matter because these are dummy indices. Okay, so this term is what we'll call R3. And you see that it always has a positive sign because I didn't have to exchange any operators. Now, the last term, the last type of terms, is coming with a factor zeta, which is -1 for fermions. And that's the case where I put the expectation value on this pair of operators, which are, you see, in order to do this, I have to exchange two operators. And that's why I pick an odd power of zeta. And then the term looks like an expectation value of A mu dagger A lambda prime multiplied by A mu prime dagger A lambda. Okay? And this second term is called fork or exchange. Whereas the R3 is also called direct. Okay? Now, so this, I wrote it quite generally, but now there is also the first term. And now we have to specify which state I'm calculating the expectation value over. And actually, in the R3 fork approximation, you are assuming that it is the ground state of the non-interacting part of the Hamiltonian. Okay? And the non-interacting, it's the ground state of H naught. So, so if expectation values are defined as, okay, they're defined within the ground state, and the ground state of H naught is
F.
Is F, what we call F, or if I write it explicitly, it's a product of all lambdas inside the Fermi C of A lambda dagger acting on. Okay? So it has a well-defined number of particles. And this is, of course, now I'm focusing really on fermions. Okay, so the factor zeta is just -1. And in this case, the expectation value of A dagger, or AA is 0. Okay? Or in fact, any operator that doesn't have an equal number of A daggers and A's will give me 0. Okay? So for this state, we can forget about these things, and we only get two terms, the Hartree and the Fock. Okay? And the interesting thing about it is, we'll see now a concrete example for using this. I mean, here the indices were completely general. We'll see now a concrete example, and for fermions, the Fock term has an opposite sign. So it always acts against the interaction. If the interaction given to you is repulsive, like Coulomb interaction is an example, the Fock part will tend to reduce it. Okay? Okay, so let's see what it gives. For a concrete example, this is like the most mundane, most abundant, it's not, actually it's not the most abundant, sorry, it's the most, the simplest, if you like, example of applying this. Take a material that is a metal, and we look at the electrons in the metal that are, to very well approximation, are described by free electrons, and ask what happens if you add the Coulomb interactions. Okay? And we want to treat the Coulomb interactions in Hartree. And by the way, the Coulomb interactions don't have to be just the standard Coulomb interaction, V square over R. They can be screen interaction, they can be modified, doesn't matter, interaction. Okay? What we want to see what interactions do to a free electron gas. That's the question. Okay? Okay, so let's apply this. Okay. So this is, like it's an example. Well, we have H naught is just free electron gas. So the Hamiltonian is a sum over K and sigma of epsilon K, A dagger K sigma, A K sigma. So the quantum numbers, what before I called lambda, are two kinds, two labels. One is the momentum and the other is the speed. Okay? Okay, and the epsilon K is a free electron gas, so it's just the kinetic energy. Okay? This is what it is. All right, so, and we know that the ground state is a product of all K and sigma, for which K is inside the Fermi ball, okay, of A dagger K sigma acting on the vacuum. But I'm not going to use this because we already have expression for the expectation values of each two operators from the previous lectures. We know all about this. Now we do Hartree-Fock for the interaction. So first let me write the interaction itself. Using these quantum numbers, we already did it in the previous lectures, so I'm just reminding. There's a factor of half, and here I actually want to add a normalization factor, omega, which is volume. Why is that? Because the wave functions, when I write matrix element of the interaction potential, I get a Fourier transform, but there's also a normalization factor from the wave function, and it introduces this factor. Okay, it's just a normalization for keeping the units, and now I have a summation over 3 indices, k, k prime, and q, and 2 indices from the spin, because it's a density interaction, therefore the spin is summed up in all of them. And then I have the Fourier transform of the interaction Hamiltonian. VQ and A dagger K plus Q, A dagger K prime minus Q, sigma prime, A K prime, sigma prime, A K sigma. Okay? And once again, why do we have only 3 indices? Because there is conservation of momentum. I'm writing down here on the side the diagram that describes this process. So it looks like this. I have 2 incoming particles, if you like, 2 incoming electrons that are destroyed. This is what the arrows describe. They are destroyed because one of them emits a photon. Okay, this is not something I prove to you, but I'm just telling you. This is what it does. And it therefore loses momentum and is recreated with, momentum K plus Q, and this, this is K, okay, let me, just to be consistent, and of course it doesn't matter because I'm summing over all signs of Q, okay? But just to be consistent with the diagram, so this would be K minus Q, and this is K prime plus Q. And notice, by the way, that in this process, the spin doesn't change. So this is some spin sigma, and this is also sigma, and this is sigma prime, and this is sigma prime. It doesn't change, okay? Because in the process, the spin is not affected, just the momentum. And there is momentum conservation. That's why there is only 3. There are only 3. Okay. So this is what it describes, and it's interaction term. And now we do a Hartree-Fock, just the way we said before. What is Hartree-Fock? We neglect, or not neglect, but we notice that the expectation value will be calculated on the ground state of the unperturbed Hamiltonian of H naught, which is the Fermi sphere, Fermi ball actually, and therefore A dagger has 0 expectation value. So we only have the hard tree and the fork. What is the hard tree? It's the one where we put a contractor on a pair of A dagger and A's, where I don't have to exchange, and the fork will come from this. Okay, and now let's write it explicitly and see what we get. So this will give me a sum over K prime Q, sigma and sigma prime, V coulomb of Q, V of Q. And now let's open the bracket, and I write the hard tree part. I will write in blue. So it is the expectation value of A dagger K prime plus Q. Sorry, I need more space. K prime plus Q sigma prime A K prime of sigma prime, this, times what is left over after I contracted these two. I'm left with an AK plus a minus Q sigma AK sigma. Okay, that's the hard tree. Comes with a positive sign. And now I have the fork term, which comes with a minus sign. Okay, so it is this and this, A, K. So we just don't get confused with the prime. So this is an arrow. Okay, no prime. So it's K minus Q sigma, and A K prime of sigma and sigma prime expectation value, and the remaining operators I keep are this. Okay. Sorry, and I'm forgetting that what I'm writing now is already an approximation. So this is not the int, it's the hard tree fork approximation of this, which is this plus some constant. Okay, keep in mind there is a constant. Okay, so let me just finish writing it. So what did I left? I left over K prime plus Q sigma prime and A K sigma. Okay, close bracket. This is all. I have only two terms, and you see each of them gives me a correction to the single particle Hamiltonian. Why? Because these are numbers, okay? Actually, we know exactly what it is. I'll write it in a minute, but it's some number. This times the interaction. If you sum over Q and K prime, you get something that may depend only on, we'll see, okay, what it gives, but it's something that ultimately will give you some single body term, and this is the same thing, but it's a different one, okay? Now notice there is a fundamental difference between the two terms. First of all, what is, let me remind you, in any Fock state, what is, for fermions, okay, now only for fermions, what is this? Okay, when you calculate it over a Fermi C, the expectation value is over this Fermi C. No, it's zero if alpha is different from beta. But if alpha equals beta, so there is a delta. First of all, there is a delta. Okay. First of all, okay. If it was if it was okay. So actually now it depends on the okay. It's delta alpha beta, but there is also a dependence on whether alpha and beta, or actually alpha is inside or outside of the Fermi C.
Yes.
Right? So it's actually this times a theta of let's write it like this, EF minus epsilon of alpha. Okay, so it's only if it's inside the Fermi C, you get something that is non-zero. Now, actually, what is this? What is this? It's nothing but the occupation of the state alpha inside the Fermi C. Okay? Or if you like, more generally, it's the occupation of the state alpha. If it's inside the Fermi C, it's occupied. If it's not occupied. It's zero. Okay? So
now why it's epsilon alpha, not epsilon beta?
Well, there's a delta. So there's
okay.
Okay. Yes. Okay. All right. So so great. So let's apply it for our case. What do we have here? So first of all, we have a delta. A delta over both indices, both spin and k have to be the same. But you see, the spin is already diagonal. It's already the same. So the delta is now, it's a delta of k plus q. And k.
אנחנו עושים את זה הכל מצב הגראונד סטייט, או כאילו פרמיסי, או
Yes, now I said, when I write an expectation value, I have to tell you which state I'm calculating.
אנחנו פשוט להגיד שאין אלפא אחד, כי אם זה בפרמיסי,
No, so we already proved it in the previous lecture, that in the Fermi C, this thing gives you either 1 or 0, depending on whether you are inside or outside. Okay? Okay? We already showed it, so I'm using it. Of course, only for this kind of state. Okay, so that's the delta. Now,
That's supposed to be k prime.
What? No. Sorry, yes. Sorry, thank you. Both of them are k prime, yes. Yes. But actually it doesn't matter, because notice that what does this delta, so this delta in principle should have constrained somehow your indices and will reduce it when you sum over the k prime and q. But when is this delta satisfied? If q must be 0. Okay, so in fact, for any k prime, it is satisfied provided that q equals 0. So actually what it does, it actually kills the summation over q and replaces it by one term, q equals 0. Okay? So we'll use it in a minute, but before that sorry, and of course I have to here multiply it by theta of E Fermi minus ek prime. Okay? All right. What about the second term? So you see, it's actually, this is actually, this delta, the delta can be expressed as a delta of q and 0. You can forget about the k prime. Okay? And it's true for any k prime. Great. Now what about this term? Now it's you see it's less trivial because we have two deltas, one acting on k minus q must equal k prime. Okay, and now q, there is a solution for it when q is not necessarily 0. In fact, if you look at this diagram, what does it do? It forces k minus q to be equal to this k prime. Okay? Okay, but there's another delta on the sigmas. Okay? Okay, so what? No, you don't need because it's already the same.
Okay.
That's exactly the point. By the way, it means that, so how many terms here for each value of the case, you have two contributions from sigma prime equal up and down, and this whole thing will multiply this term with sigma equal up and down, okay? So, okay. Great, so now let's see what we get after we plug it in. With your permission, I'm now erasing this. We need it. And this is what we get. So the Hartree-Fock approximation of interaction becomes, let me write it like this. It's Hartree plus Fock. And I'm writing them each one by one, okay? Let's first write the Hartree part. Okay, so what is it? So I have a delta of q equals 0. So it gives me 1 over 2 omega. And now I have a sum over k prime. And here I have to replace this by v of 0. But because it's a constant, it's only one term, let me just put it here. Okay? And what am I left with? I'm left with, I still have, notice I still have a sum over sigma and sigma prime. The delta doesn't kill any of them. And I have a sum over k and k prime, sigma and sigma prime, actually, you know what? Sorry. Let me rewrite the sum. First I sum over k prime and sigma prime. And this gives me a theta of E Fermi minus epsilon k prime for each k prime and each sigma prime. Okay, so this is, I plug this expression here, and I did the summation first only over k prime and sigma prime, and I still have a sum over k and sigma of whatever is left. Whatever is left is this, okay? But Q equals 0. So it's actually just AK sigma dagger AK sigma. Okay? Now this is great because, and you know, instead of writing the theta, I could just write occupation of the state k prime sigma, okay, inside the Fermi seed. So what did I get? This is a constant, okay? Actually, for Bell-Coulomb interaction, it's kind of divergent, but let's not worry about it, because in reality there is, okay, let's soon interpret this thing and see what it does. But what is this? First of all, it's a number, okay? Moreover, what is it? It's not just a number, it's the number of electrons. It's just a total number of electrons in the system. Okay, so it is just n. Just the number of electrons. Actually, when I divide it by the volume, I get the density of electrons. Okay, which, as you know, in metals it's a constant. It's order the Avogadro number. Okay, per unit square cube, centimeter cube, sorry. Okay. And all of this multiplies something that looks like what is now. This is an operator. It's not a number, but what operator is it? Yes, it's the number operator, right? Okay. So what does it describe really? And this is like the simplest or the crudest mean field approximation you can say. How can you interpret it? Each electron here gets some shift of energy from this constant. Notice it's a constant. It's outside of the sum over k, so it's not even dependent on k. It's just a correction to the kinetic energy for each electron. But what is this number? It's actually a huge number. It's just the total potential because of the negative charge of all the other electrons. Okay? So if you think you have an electron gas and there's a Coulomb interaction, so in the mean field approximation, you replace all the other electrons by a chunk of, a huge macroscopic chunk of negative charge. This is what it means, okay? And in fact, notice that if I take expectation value of this, which will also turn this into the number, I get an n squared times something. What does it remind you of? No, I mean something really classical. It's like a capacitor, okay? It's like a capacitor, okay? This is what it is. Now, it's actually, you may say, oh, but this is terrible. Obviously, it's not perturbative in any way you can think, because it's a huge energy scale, Coulomb interaction of a macroscopic number of electrons. But of course, why shouldn't we worry about it? Let's just think now physics, forget about operators and everything. And I remind you what I'm talking about. I'm talking about electrons, not in a vacuum, but in a metal, in a solid state. Solid state, a metal, at equilibrium, is a stable material. Why is it stable? Electrically. לא זזים. אפילו, what?
The ions,
Exactly. There is the material, the matter is neutral, electrically neutral. For each electron, you have a positive charge that otherwise it would fall apart, obviously, right? You cannot have a capacitance of other centimeters. Yeah?
Can you explain why it looks like a capacitor?
Yeah, because the energy of a capacitor, you just take, what is a capacitor? It doesn't matter what's the shape. It's some device where you put charge, okay, and there is the energy, potential energy of the charge capacitor is Q squared over C, right? Remember? So this V of 0, it's like 1 over C. If you like that, okay? That's what I mean. So it's the capacitor is an approximation where you take all the extra charges and treat them as just electrostatics. That's what it is. But when we talk about a neutral material, although this term by itself is huge, it's exactly cancelled. Or if you like, almost exactly, because the ions are not just uniform, but again, you can do a mean field approximation. It's cancelled by the positive background. Okay? And therefore, you can forget about it. Okay? It cancels. So there is only one correction that is important, and that one actually comes from the Fock term. And it's negative. Amazing, okay? So to leading order in perturbation theory, a repulsive Coulomb interaction gives you a negative correction to the energy. Okay? Unless we will see what happens, okay? So there's something you have to worry. I mean, of course, it will be like that as long as the approximation is justified, which means that the corrections have to be small in some sense. Okay, so let's write the Fock term. So now it is less trivial because here the delta acts on the K prime has to equal K minus Q. Okay? So what it does, it can either eliminate the Q or the K prime. Let's eliminate the K prime and replace it everywhere by K minus Q. Okay? So we're going to get, let me copy first we have a sum over, let me be a little careful here. I want to sum over K and sigma, and then some, I'm deliberately replacing it, sorry. Q and Q. Okay, and I no longer have another sigma prime. Why? Because there is also a delta sigma prime. So notice there are less terms in terms of the spins. I'm getting a contribution only if sigma equals sigma prime. Okay, so the summation now will have only factor sigma, and if it's degenerate in spin, it will give you a factor of 2 and not a factor of 4. Okay, it's very important to notice. And this is it now. So what is left inside the sum? first there is the VE of Q, and then, and sorry, I didn't finish writing. What I have here is the occupation of what? Of K minus Q and sigma. Okay? It's the occupation, which is the theta of the Fermi, etc. Okay, so this is what I have here. It's I have occupation of K minus Q. And this is all a number, which I'm going to encircle, right? That's why, and what is left over? The operators. A dagger K prime plus Q, sigma prime, A K sigma. But we use the delta. First of all, there's a delta of sigma sigma prime. So this sigma prime equals sigma. But in addition, K prime equals K minus Q plus Q gives you K, just K. So once again, it is AK sigma dagger, AK sigma. You see? So that's really nice because we again we don't have to find another basis and diagonalize it. Not only this is a single body Hamiltonian, it is still diagonal in the same basis. Okay. Now here, what I forgot something very important. What I forgot? Minus. Yes. Right. So there is what? Yeah. Let's put it here. Yes. So it's negative. Okay, this is all, this is positive, this is positive. And in fact, we can rewrite it. No, okay. Erase all this. So let's rewrite it. So it's a minus. Let me write it like this. It's a minus sum over K and sigma of delta K. A dagger K sigma, A K sigma. Okay, where delta, now that's a definition. Is the sum over Q, V of Q, N of K minus Q. Okay, and actually the sigma, it doesn't depend explicitly on the sigma because in the Fermi C you have both spins. Okay? This is what it is. And it gives some negative correction to the single particle energy. Okay? So if you like, the total energy per part, the total epsilon K.
You forgot the volume.
The volume is, you're right. Actually, there is also a factor of half. Yes, thank you. Okay, and of course, this has the correct units. It has units of energy. Okay, so and now there's a way to calculate it. I'm not doing it. It depends, of course, on the dimensions, etc. But I'll give you the result, and the result is very interesting. First of all, what does it mean? What does this result mean? It means that for each electron, the epsilon k, now the epsilon k, modified epsilon k, is, let me write it like this, it's epsilon k 0, which is, this is the usual kinetic energy, plus the Fock correction, which is, okay, let me just write it directly, which is minus delta k, okay? And this has some dependence on k, which is not so trivial to see, but what is more interesting to look at, if now I'm saying, okay, so my ground state is still the same ground state I had before. I didn't have to modify the ground state. I see that it works nicely, except that now I have corrections to the energy, and the corrections are even negative because of this cancellation with the positive background. So what is the ground state? It's the full Fermi sea, full Fermi ball. And if I want to calculate the total energy per particle, I just have to sum over all k's up to k Fermi, okay? So this will already be a meaningful thing. So let's write down the calculation. I'm only erasing. Okay.
Thank you.
Okay, so let me write it here. Okay, so the energy per particle, actually, if you like, it's the ground state energy per particle. I denote it just by epsilon, but the definition is really expectation value of the energy of the per particle, okay? So what is it? It's combined of two terms. One is the kinetic part from the free electron gas. Let me call it epsilon k for kinetic. Plus epsilon exchange, which is the total contribution of exchange energy, and it is nothing but a sum over the deltas. Okay, it's a sum over all the deltas. What are they? Epsilon k is, hope you remember from your undergraduate or I don't know, actually. Do you remember this? Or statistical mechanics? Okay, it's just what you get if you sum k epsilon k. Well, epsilon k is this, right? And if you do the summation in 3 dimensions, you get a factor of 3/5 because it's You have to go to spherical coordinates, blah, blah, blah. Okay. I don't remember, I'm just telling you. But it's a very easy calculation that you should have done some time ago. And then actually let me write it explicitly. So the 3/5 is not so important. What is important for me is the parameters that determine this are what is E Fermi. It's h bar square kf square over 2m. Okay? Okay. What is the exchange energy? So once again, it's a minus sum over delta. Sorry, sum over k of deltas, where k is again with k smaller than kf. There's a factor of 2 because of the spin. Okay? That's what it is, and it's negative. And let me tell you the result of the calculation. Again, it's for 3 dimensions. It gives, so there is a factor of 3 over 4 pi times E squared times kf. Now I want you to look at it and tell me the following. So what will be the total energy? This plus this gives you a positive minus some negative correction. And the question is whether the negative is that big or that it can cancel it and turn it over, okay?
What's that? Epsilon EX.
So, epsilon again. I did a Hartley fork, and I get that the Hartley part I said I can throw away. The exchange part for each electron it gives me an energy delta. Or minus delta, but I have to sum over all the deltas, and then I just get the total, just like this one, the first term is the sum over k and the factor of 2 for the spin of epsilon k, or epsilon fs. Epsilon, okay? That's what it is.
Okay, so
Okay, so I get, and notice the two expressions depend on kf. Okay, and in fact, the question you have to ask yourself, when is the approximation justified? Because I'm telling you the approximation is justified if the interaction is, in a sense, small. Okay, because if it's not small, the corrections that I throw away, it's not justified. Or I have to work harder to show that maybe it's justified if I resum them in some way. Actually, that's what happens, okay? In reality, there are corrections that are by themselves not negligible, but if you sum them, an infinite sum correctly, you get that it's fine, okay? I don't have time to do it, unfortunately. In this course, it's a bit shortened for this. But what I can is, what I do want to show you is, let us look for a criterion when is this correction small enough compared to the bare kinetic energy. So basically, one can define a parameter. It's named Rs, it's a dimensionless parameter. And it is defined as, I'm forgetting about the pre-factors here, the 3/4 pi and all that. It's just a ratio of two energy scales. Now, by the way, how can you easily see that this is indeed the energy scale? Let's see if you can see can you give it a simple interpretation? You see that it has E squared, which is good, okay? What is the Coulomb? So Coulomb interaction, I remind you, is E squared over R. Okay? So what is this? Kf has units of 1 over some length, okay? And therefore it's okay with the units because it's E squared over some length. But what is this length? Okay, so let me remind you another thing that you forgot from free electron dust. There is an expression for the density, which is in 3 dimensions, it's Kf cubed over, I think if I'm not mistaken, it's 3 pi squared. Remember this? This is the density of electrons in a metal, in a free electron gas with Fermi energy or Fermi momentum Kf. Okay, so the density of particles is actually proportional to Kf cubed. Okay, and Kf cubed, the Kf is the Fermi momentum is of order the inverse of an angstrom. So what is 1 over Kf? This will give me a length scale. Let me call it R0. And it's of order an angstrom. What is it? It's the mean, that's density. What is density? It's the number of particles per volume. Okay? So it actually goes like the inverse of the distance or the average distance between particles to the power 3, right? So R naught or 1 over Kf is actually the average distance between 2 electrons in a metal. Okay? That's what it is. And therefore, it's not surprisingly, that's the scale of the Coulomb interaction. Okay? So Rs that you can define as the ratio between the Coulomb interaction, which is actually given by this E squared over R naught, divided by the kinetic energy scale, which is E Fermi, or explicitly h bar Kf squared over 2m. Okay? That's basically the ratio between Coulomb energy on the average and kinetic energy. Now, what happens if this ratio is, what is the criterion for the interaction being perturbative? That it will be much smaller than 1, right? So, Rs smaller than 1 is perturbative limit. That's where we're sure that the approximation is fine. But it turns out that this is actually never satisfied. So if you look at the real numbers, I'm not giving you numbers, but you can do it for yourself and look at up in the literature. What do you get for metals? For metals, just that we thought that we can throw away Coulomb interaction. It's actually of order 1, maybe even 2. So it's not negligible, but nevertheless, the reason the perturbation theory works is more sophisticated than just throwing away the other corrections. Okay? This is for metals, but in materials that are not metals, that are some oxides, with heavy elements, all those more interesting materials, very often this is not even small. Okay, it can be actually larger than 1, of order 10 or more. So what happens then? Then it's not clear that this works, and in fact, what really happens is that typically in such materials, the metallic state, the free electron gas-like, is not the true ground state. It just breaks down, and then you have a new ground state. What is going to be now depends on many other things, but one of the things that can happen, and that was already realized many years ago, it's not even very modern, is that there is so in fact, if in some way you can quantify the two terms in terms of this dimensionless parameter Rs, and you can write it as some constant, some fundamental constant times, this will go like 1 over Rs squared, and this will like 1 over Rs, and if Rs is not small, the interaction energy wins, and then what it does is to create a so-called Wigner crystal, which is the electrons, instead of forming a fluid or a gas with a bit of interaction, they form a crystal, okay? Not related to the lattice crystal of the solid, but they form a crystal, okay? And then the interaction dominates, that keeps them apart. And usually it happens when Kf is actually sufficiently big, sufficiently small. When Kf is sufficiently small, that's what you get. Okay, so I'm just, it's beyond the course, but I'm just mentioning that there is some instability. And naively, you can already see it from the fact that if the correction energy wins, then you are in trouble. Okay? Because you cannot have a total, kinetic energy is not enough to sustain the interaction, basically. Okay? Okay, so I think this is where I stopped talking about the art of folk, because I don't think I have time for the part that I said, higher order in perturbation theory. Any questions about this before we switch to the next example?
לגבי המעבר מ-E external ל-RS.
It's not external, it's exchange.
Okay, exchange. צודק. איך ביצענו את המעבר משם ל-RS? מאיפה RS צספת?
so I got something for this, and I got something for EK. And RS is just the ratio of between this and this. I'm forgetting about the numbers because the numbers are of order 1 for me.
אוקיי, ולמה אנחנו, איפה הכנסת את אינטראקציית קולון פה לתוך הדבר הזה?
No, this comes from the I forgot to say that this particular result. Okay, this there's something I want to just avoid misunderstanding. This expression is general, with VQ being the Fourier transform of whatever is in the interaction potential. But if the interaction is Coulomb, namely in real space it's E squared over R, This is then VQ is 4 pi E square over Q square. So you have to plug it into this and compute what it gives you when you sum over Q up to K epsilon of K minus Q equal Fermi and so on. It's not a trivial calculation with the Legendre transform, never mind. There are tricks to calculate it analytically for 3 dimensions, okay? And then you get, and this I'm just telling you, this is what you get, okay? That's a final result, yeah?
Could you explain again why an arbitrary term is 0?
It's not 0, it's huge, but it cancels with the positive background. So the Hartley term just gives you, per electron, it gives you a potential, a huge negative, a huge potential energy that comes from repulsion from the total charge of all the other electrons. Okay?
Okay. Why we don't wear it in?
Because there is another very big contribution which is equal to that, but with a plus sign or with a minus sign.
Okay.
Because it's attracted to the ions. Okay, the ions have positive charge. Okay, and on the average, the material is uniform, and you get a huge positive charge compensated by huge negative charge, and this you can throw away, right? Otherwise, we wouldn't have materials at all. Okay?
So this approximation is not good for electrons in metal?
No, it's excellent for.
No, it's not.
Okay, first of all, once again, the Hartley part is not perturbative, but because it's trivial, it cancels. Okay, it's like a capacitor, but if you add to it from the beginning, the total. If you add from the beginning the potential of the ions, then you don't even have to worry. You see the cancellation immediately. Okay. Actually, often when you write the model for interactions in metals, you write the sum over Q different from 0, because you eliminate the 0 component. Exactly for that reason. Okay? And then you don't even have it, just 0. Okay? Now, I'm saying that the Fock term, on the other hand, is not 0, it's not negligible, gives you a correction. The correction may naively not be so small as you like, but nevertheless there is a reason that it's justified to neglect the corrections. And the reason is not that they're smaller, but that if you sum them together, you see that altogether they reduce the result of the original interaction, and this is an effect called screening. Okay. Now I'm not doing a calculation. Let me just give the physics. Okay. If you throw a charge into a metal, a test charge, let's say positive, the metal is approximated by a free electron gas. So what happens to the other electrons? They are repelled from it. Sorry, if it's positive, they are attracted, right? So you have a positive charge, and what happens to the electrons? They will be gravitating to it, trying to and then, but what happens when the electrons attracted to it? They will reduce the total charge, right? And they will screen it. Okay, and as a result, there is going to be an effective charge that is smaller. And there is some length scale that is called a screening length. And it describes the decay of the charge away. And then if you look long distance from this, actually the interaction that you see is not E squared over R, but it's going to be E squared over R times some exponential, a Yukawa potential. That's in 3 dimensions. In lower dimensions, it's not so obvious. Actually, it can. The interactions in low dimensions are definitely not photomaterial. Absolutely not. Okay. But in 3-dimensional metals, the result is overall it's perturbative, but not for the naive reason that the first order in perturbation theory is small. Okay? Now, of course, all what I said here in words, you can translate to diagrams and equations. One thing that, let me just, before we go to a break, I want to give you a hint of how to use the diagrams. So I didn't use diagrams to calculate the Hartree-Fock energy because it's relatively simple in this particular case. But as a matter of principle, I could associate it with 2 diagrams. And I'm using this diagram to describe the interaction, the term in the interaction. Now, as it stands, it describes an operator, if you like, that is one of the operators that appear in the interaction. If I want to know the Hartree or Fock energy, I have to put it in an expectation value, okay? So the expectation value for the interaction is going to be a sum of 2 contributions from the Hartree and the Fock, which you can, so let me call it, just writing it like this, but without the head side, because it's already an expectation value. Okay, maybe let's just put an expectation value so that we will not get confused. Now, what is, and each of these, I want to represent with a diagram. Okay, so let's first draw the diagram for the Hartree term, okay? So we have this interaction. Sorry, I'll plot it over here. So I take this interaction and I want to put expectation value on it. What does it mean graphically to calculate an expectation value? I will close some of the external legs into a loop, okay? And what does it mean to close it? It means to put a delta on it, right? Because then it forces it to be the same, okay? So in the Hartree part, I'm taking this line and connect it to this. Okay, so that K minus Q must equal K. And similarly, K prime plus Q must equal K prime. Okay? But then if I do this, then K must be equal K minus Q, and therefore Q must be equal 0. Okay? So the result of this, let me draw the result. The result will look like this. There will be a closed loop with K, which corresponds actually to the expectation value of AK dagger AK. Then there is a V of 0. Okay, that's the wiggly line. It's a number, and then there's another loop that is, and here there's K, and here there's K prime. Okay, I'm now a bit uncareful with the spins. They just give you some factors of 4, right? Because this has to be multiplied by 2 and this by 2, so overall it's 4. All right, so that's what it is. That's a diagram that describes graphically the heart rate. And if you want to translate it to a calculation, then actually here I have to sum over k, multiply by the spin degeneracy, and I also have to sum over k prime and multiply by the spin degeneracy. I multiply this by v of 0, and I get the Hartree result, which is just n squared times vq. Okay? That's basically what it is. Now, what is the Hartree? Using the same logic, I have to close the legs. So I will draw it on the same diagram, but I will force the legs to close in a different way. And now this is no longer equal 0. Okay? Great. So how can I close the legs? So instead of closing the loops here, I associate k minus q with k prime. Okay, so I'm taking this like that. Okay? It's one loop. The second loop is to calculate the expectation value. I take k prime plus q and connect it to k. Okay? You understand what I'm plotting? Let me just do it like this. Okay? So there are two different loops. One like this, one like this, and this remains a v of q for any q. And you have to also sum over q here. So what did I get? It's a bit hard to see because notice that what I got here is, think of it as, sorry I don't have rubber bands to show you, but I'm allowed to fold it up, so it's going to be one line, a wiggly line, and another line, or if I write it in a simple way, it will look like this. There's this wiggly line. There's a k, or a k minus q, and a k. Okay, that's the diagram. And what does it mean in terms of calculation? So whenever I see a loop like this, I have to sum over k and q, and put a factor of 2 for the spin, v of q, and n of k minus q, n of k. Okay? That's what each line means, n of k plus 2, and vq, and I have to calculate the sum, solve an integral or whatever, that's the result. Okay? So this is a graphic language. Now, why is it useful? Just give you a hint and we'll go for a break. If I want to go to higher order in perturbation theory, what does it mean higher order in perturbation theory? The first order, I only have one factor of v of q. If I do perturbation theory on the interaction, I want to have v squared, v cubed, v to the 4. So I need to, so instead of writing expressions, very long ones, they're going to become long very quickly. Let's draw diagrams. And the diagrams are all the possible graphs that you can plot with more than one wiggly line. So for example, in second order, you can have a diagram that looks like this. This is now a K and K prime and K minus Q, K prime plus Q, but in the middle this is Q, and here you have some K and K plus Q, or something like this. You have to satisfy momentum conservation at each junction in the graph. But this, for example, will give you the leading, I don't tell you why, but it will give you the leading contribution in second order in perturbation theory, but there are others, like you can put two wiggly lines like that. It's also allowed. It will be less important, but it's there. And in a higher order, you get more bubbles or more lines like this, or all the combinations. But you can prove that some of them will dominate, and that's where, if you sum them to infinity, you will get the screening effect magically. Okay? But to see how to classify the terms, it's better to draw diagrams instead of writing. Each diagram is a huge expression. Okay? Okay, let's stop here. So the next thing I'm going to do is give you another example for a mean field theory that is less trivial. And in what sense it's less trivial? What we saw in the Hartley fork is that basically the interaction, which was repulsive interaction, that's what we had in mind, it didn't modify the form of the ground state. The ground state remained a Fock state, Fermi C, and it's just that the energies were different. Okay, so we started from H naught, that is diagonal, the basis of K and sigma, and we got back something that is of the same form, only with different energies. Okay, so in that sense, that example is a bit trivial. And now we'll see an example where that's not the case. And the difference in the model that we take is that instead of repulsive interaction, we have attractive interaction. Okay? Now, how can you get attractive interactions between electrons, for example? I mean, first of all, you can have attractive interactions between particles in various instances, but even electrons in a metal can develop attraction because of interactions with phonons, because of all sorts of things. I'm not getting into this, but it is there, okay? And what I want to show you in this example, that once you put an attractive interaction, always, doesn't matter where it comes from. If the non-interacting state is just a metal, it's always getting unstable to this interaction. So unlike repulsive interactions that only modify the energies to one extent or another, attractive interaction, even if it's small, if you go to the true ground state and cool down to 0 temperature, you will no longer find a metal. You will find another phase of metal. Okay, and unless something else intervenes, but if it's just that, that's the case. Okay, and the ground state it has is very different, and in fact, it's going to give superconductivity. So the model that we're looking at is going to be a BCS model for superconductivity. this is the context where it was originally developed by Bardeen, Cooper, and Schrieffer. This is named after them. But of course, the model is more general and it applies to many cases. Okay, so what is the idea? So I'm going to write down once again a Hamiltonian that has a non-interacting single body term plus interaction. Keep the notations the same, so the interaction. But now, the H naught is actually the same as what we had before, just free electron gas. But one thing that I want now to keep, I want to measure the energies not with respect to zero, but with respect to the Fermi energy. Okay, so the non-interacting system has a Fermi energy, and when I'm writing the single body Hamiltonian, I have a sum over k and sigma just like before, and here I have some energies that I call psi of k, c dagger k sigma, ck sigma. I also denote the electronic creation annihilation by c and not a. Why? Just because it appears like that in the literature. Okay, I'm allowed to choose any letter I want, as long as I work with only one type.
זה אופרטור היצירה והשמדה, שהוא לא אופרטור שקוראים לו פרמיסטי.
לא. זה אותו דבר, רק שם אחר. אוקיי? Don't get confused. I use different
כמו
notation.
כמו שהבוזונים.
Another name for A. Okay? C is what before was A, but now we are a different hour, we had a break, let's change notation, okay? No, you have to get used to it because every book you open, depending on the subject, the notations may change. What can I say? So sometimes you denote electron operators by C for conduction, okay?
אנחנו פה עם פרמיונים או עם בוזונים?
For fermion, electrons are fermions.
כן.
Okay, no bosons today, as much as I like them. Okay, now what is the psi? So psi is epsilon k. This is just the usual kinetic energy, if you like h bar square, k square over 2m, minus EF. So it is just a definition. It measures relative to the Fermi energy. Okay, so in a sense, actually, by subtracting EF, what am I doing? It is equivalent to taking a Hamiltonian and turning it into the grand canonical Hamiltonian. Okay, so which is usually more convenient to work with if you do statistical physics. Okay, go to the grand canonical and then you subtract.
Zero temperature.
At zero temperature, mu equals EF. That's okay, and we are doing now zero temperature. Okay. In any case, I mean, we can do finite temperature, but it's not. I mean, the course is still in quantum mechanics, so I'm looking at ground states and okay. Good. So this is just the definition. Now, notice that because of this. Although the epsilon k's may always be positive, they're just kinetic energy, psi can be negative or positive depending on whether you are above or below the Fermi energy. Okay? So that is already a notation that allows you to treat electrons and holes equally in some sense. Okay? Okay. Okay, so that's the model, first of all. And now the interaction. So the interaction, I just first remind you the general form of interaction when we write it in the K basis. It has the following form. It's a sum over K, K prime Q, sigma prime, and then we have V of Q, and C dagger K plus Q, C dagger K prime minus Q, okay, vectors here, C K prime, sigma prime, C K, sigma. Okay, that's a general interaction term. And now I'm taking now an interaction that, first of all, it's attractive. So there it's a minus times some positive number. And I also want to assume for simplicity that V of R, let me first write what is the potential, interaction potential that I'm assuming, and then we'll turn it into Q space. So it's minus V times a delta. Okay, so it's very short range. It's a contact interaction. Okay, it's effective only when the particles are close to each other to some microscopic distance. And here there's a minus sign where V is positive parameter. Okay? Now, why did I choose a delta function in real space? Because when you go to Q space, what is the potential? What is the Fourier transform of a delta? It's a constant. No, the Fourier transform of the function delta is a constant. Okay? Okay? So, and therefore in Q space it's very convenient. We just, it's just a constant. We can take it outside of the sum. Okay? And now we have a summation over all these indices, but in the BCS model, and I mentioned to you a few lectures ago that you can classify the interaction according to various choices of the indices. There was one term that I didn't explicitly write because it really appears very naturally when you go to K and sigma space, not to lattice site index basis. And that's the following term, and I emphasize that the interaction also includes other terms. Okay, it may include other terms. Maybe some of them will even have positive sign, and in which case we can deal with them using the R3 fork that we did before, and all it will do is to change the size to some effective size. Okay, and this is taken care of, but this particular part of the interaction that BCS have accounted for, it is the following. And this is what we'll take in our model. So we are not using this. We're using a term, a particular case of this, with first of all, V of Q is a constant, and second, we choose a particular partitioning of the K and K prime, etc. And it has the following form. Minus V times are going to be only two indices, K and K prime, and the spins. Okay, and it looks like this. It's a K Okay. Just look for a minute. Okay. What's this thing? Okay, so now if you like, it's like Q equals 0. Yeah, it's like a Q equals 0. But anyway, V of Q is a constant, and we take it outside of the sum, and it's independent on K and K prime. Okay, that's the interaction. And now I'm going to do the following. I want to do a mean field on this. Before we saw that when we do mean field in the usual way, assuming that the ground state haven't changed from what it was before, we had Hartree-Fock because there were two terms that we threw out. These were the cases where you put expectation value on C dagger, and C, right? And that's always 0 if you assume a ground state that has a well-defined number of particles. Then these things can never have an expectation value. Okay? Now let's allow it to have a finite expectation value. Okay? What I mean by that is I'm assuming a new ground state that at the moment I don't know what it is, but I know that it must have a particle number that is not well defined. Okay, so if I want to write it in terms of the Fock states basis, it will be some expansion with different numbers of particles. Okay? But at the moment I'm not specifying it. I'm just assuming that I have a new expectation value, which means, again, it's a new ground state where this thing is non-zero, but it's not just anything. It will be non-zero for particular choice of K prime and sigma prime. Okay? So this is something that now at the moment you don't see the motivation for it. You need to have some experience and some background to arrive to it. Okay, so when BCS, they didn't start from the way I'm teaching you. Okay. They started from other things. They also started from experimental motivation, that there was some phenomena that they wanted to explain. But it represents the idea behind how to use the mean field theory. And essentially what it is it's very biased. You make a guess, okay? You make a guess that there is some expectation value that doesn't vanish. It may not be the conventional thing. And you work out to see if, and at the end you will have to convince yourself that it gave you a consistent theory, okay? maybe the guess was wrong, okay? So if you start from this and work out, solve the effective single body Hamiltonian, and then you get something that gives you a contradiction, then you fail, okay? But if it works, you discover the new state of matter that maybe have a lower energy than your free Fermi gas, okay? And that's what indeed happens in this case, once again, only provided that the interaction is attractive. Okay, so this kind of unusual or anomalous density element, matrix element, is called an order parameter, because if it's non-zero, it suggests that there is some new order, something that is representing a new phase. Okay, so I'm making now an assumption on it. First of all, it's non-zero provided that k equals to minus k prime and sigma equals minus sigma prime. And if these are satisfied, let me call this phi of k. Okay? Actually, phi of k independent of sigma, okay, because they're only two. Now, what does it mean? So when k equals minus k prime and sigma equals minus a prime, so basically what it tells me is that C dagger, wait, let me just, let me call it, sorry, just so that I will be consistent with my own notations. Let me call this phi star, okay? There's an important point that I have to make before I'm writing it.
Phi is number?
So phi is a number, but since I put your star, it means that generally it doesn't have to be, but it can be a complex number. In fact, in principle, it is a complex number. Now, why do I say it? Why wasn't it the case for the expectation value of a C dagger C, which is just a number? Number must be a real number. But here, notice that it's an expectation value of two creation operators.
Not a Hermitian operator.
First of all, it's not Hermitian, that's right.
It's okay.
So it's okay, right? It's not Hermitian, and therefore, and in fact, it might have a phase. So it's a complex number, and notice that the phase is somehow, it may be related to a global phase of the fermionic operators, right? Because remember, when C dagger acts on the vacuum, it creates a wave function of an electron. And the wave function is always defined up to some global phase factor. So that phase factor may affect the number, but it's a complex number. And what it basically says is it's the expectation value of two creation operators with opposite momentum and opposite spin. And only that is non-zero. Okay? So in a sense, what does it describe? Imagine that you are creating a pair of, you take out of your Fermi C two particles, two electrons with opposite momentum and opposite spins. And you somehow bind them together or whatever, you make a pair, okay? And this pair is described by this operator, okay? So it's non-Hermitian, that's right. Okay, so it's really unusual that it has an expectation value, but within our assumption about that there is some unusual ground state, it can be. Okay? Okay. Great. So let's see what we get from it. And of course, if this is phi, then what will be the let me write now down the if this is phi k star, then if I take the Hermitian conjugate of it, what is the Hermitian conjugate of this? It's CC, and it also reverse the order of the indices. So this is phi. Okay? Because it's just a complex conjugate. Okay, excellent. Now let me rewrite the Hamiltonian, assuming that these phi's are not zero. Okay. בסדר? Okay, so then what I'm getting is an approximation, but once again, it's I call it HBCS, and it's given by, there is some constant that I have to warn you always is there when you do this mean field, and in the tutorial, Sarah will actually derive what exactly it is, because it may be important if you want to know what is the final ground state. But I ignore it for the moment, and I'm left with H naught plus H plus let me call it BCS approximation to the interaction. And now let me write H naught again. H naught, I already wrote it, but I will now rewrite it a little differently. Okay, just for simplicity of notation later. So what is H naught? First of all, it's a sum over K and sigma of this. Okay. Now I want to keep the sum over K, but explicitly introduce the sigma. Okay, why? I want to do it. We'll see why. So I have a sum over K of psi K, and for each K, I have two terms, C dagger K up, CK up, plus C dagger K down, CK down. Okay? You agree? Nothing wrong with that. Okay? Now I want to take another step. And notice that psi of K is symmetric between K going to minus K. Okay, let me rewrite explicitly what it is. This is psi, where epsilon K is the kinetic energy, so it's proportional to K squared, and therefore it's the same for K and minus K. Right? So that means that I can redefine, I can apply it, a reflection on the K's and put a minus sign on this without changing the sign. Okay? And then I will get the following expression. I'll get sum over k, psi k, ck up, ck up, plus the second term, sorry, I can just, I don't have to write the sum again. Now I'm writing C dagger minus k down, C minus k down. Okay? You agree that I'm allowed to do it. Why am I allowed? Because in the second term, I changed all the k's to minus k, but that doesn't change the prefactor, so it's correct. Okay? Now, why did I write it like this? Because you see that now I want to have combinations that always have some k and it's minus 1, minus k, and spin up and spin down. Okay? In other words, I can actually define a single index. That's just a definition. So this will be k and up, and minus k will denote minus k and down. Okay? So this k embeds both the spin and the momentum together to be something that I either have a plus or minus. And when I write it like this, I'm actually summing over both, right? Okay. So in fact, I can write it as sum over k of psi of k c dagger k ck plus c minus k c minus k. Okay? All right. Great. So very good. So now the next step is. So I define them in such a way that the second term has some. If this was some k and spin up, whatever it was, this is both minus k and it's actually. They are related, each of these terms, the indices are related by time reversal, a time reversal transformation, okay? Because you reverse the momentum and you reverse the speed. Okay?
time reversal?
Yes.
ספין זה לא קשור לזמן.
Spin is time reversal symmetry, changes magnetic field B to minus B, spin up to spin down, okay? Because the spin is like an angular momentum, right? So just remind me, okay? בסדר?
לא, כאילו אני אגיד לך.
Time reversal symmetry, some time reversal transformation, turn spin up to spin down.
אוקיי, והיא גם מחליפה את התנה מלמעלה למטה?
Yes?
אוקיי, בסדר.
Okay? Okay. You see, I'm working very hard on the H naught, but it's important because I want to bring it to some very compact form, and I need this. These are all very trivial stages. Now there's another step I can make, which is when I see something like this, I have a C dagger C. I can always switch between them, right? But then I can use basically the anti-commutators of the fermions. And replace this by a constant, right? Because notice they have the same index, right? So this is equal to 1 minus C minus K, C dagger minus K. Okay? Why do I want to do it? You'll see in a minute, but I'm allowed. Okay? These are all identities. Okay, so now, yeah, this. It for the moment, and now, what does it give me? The one is not an operator, just 1 times psi, so I get some correction to the constant, which is a sum over k of the psi k. Okay? So I get something like that. Okay, maybe it's even big, but it doesn't matter. That's a constant. Okay? Plus whatever I left with, and that's the part that I want to keep, because the constant I can throw away into the other constant, which I still didn't derive. So it's going to be a sum over k of psi k c dagger k c k minus psi k C minus K, C dagger minus K. Okay? So what have I done here? Basically, when I switch between C and C dagger, it's like changing between an electron and a hole. So the first term describes a particle-like part, and the second part with a negative energy. Notice that psi is defined with respect to the Fermi energy. Okay, so so it has an opposite sign, and it actually describes if it has it describes holes. Okay, so C dagger is the annihilation operator of a hole. Okay. Okay, so this is just algebra, but we're going to use it. That's the form we'll keep for the H naught. And now let's work on the interaction. Okay, so let me copy it. Yeah, let me copy it here. Up to a constant. I have sum over k of psi k c dagger k c k minus the same psi k c minus k c minus k dagger. Okay? All right. Now let's work on the interaction. And I'm using the fact that I assume that C minus K in my new notation, C minus K, CK, expectation value is not, this is non-zero, okay? And it's equal to what I denoted by 5, okay? All right? And phi CK dagger C minus K dagger is phi star. Okay, and now I now define something that I call delta to be V. Okay, V is the, oh, I erased the interaction. So let me write it on this side. So the interaction was minus v times. Now if I use my new notation, it's sum over k and k prime without, so the k and k primes are of this type. And now I have something like that. K prime. Okay. Actually, I also have other things, but this is the term that I want to keep because it will give me something non-zero. Otherwise, all these expectation values will vanish. Okay?
You forget the Tegel.
Yes, you're right. Yes?
Before it, you write it with sigma.
Yeah, so the sigma is embedded in the notation. Okay, up to maybe there's a factor of 2, but never mind. Okay, but then what I get now, let me make a definition. Delta is v times the sum over k of this phi k. Okay, it's a definition. Well, phi k is this non-trivial expectation value. And you see that if I'm now going back to the interaction and, sorry. This is a bit, okay. Let me just call it the interaction because I still didn't make the approximation. Here I still have operators, okay? So I don't want to put the BCS will be the mean field result. It will be with the expectation values. Okay? So this is just a term in the interaction. But now what I'm doing, I'm putting expectation values on either these two or these two. This will give me, so each of them will give me a phi k, and when I sum over k and multiply by v, I get a delta, okay? So with this definition, and of course, delta star, so delta once again, it can be a complex number in general. It's going to be the v delta star is the same v, which is real, times phi k star. Okay? So delta comes from putting expectation value on the CC and the delta star on the C dagger. Okay? And then I get.
What with the C dagger and C expectation value?
C dagger C, it's just occupation. That all that is will give you some Hartree fork. I already included it, if you like, in the definition of epsilon.
Okay.
Okay.
In the constant.
Right. It's not just in the constant, maybe even in the Hartree fork correction too. So the epsilons may not be exactly this. It will have correction, but. We're not going to use the explicit form of epsilon anyway. Okay? So for that reason, I don't care about it. Okay? It's just whatever I have in a method. Okay?
זאת אומרת, זה יכלול גם את n בעצם באיזושהי תצורה מסוימת? או זה יכלול בעצם עוד את n למשל בצורה מסוימת אפסילון?
Yeah, it's the same thing we did before. It's already included. As we saw, we didn't do anything. We just changed the energies. Okay? But what the new thing here is that I add another term because I allow expectation values that before vanished. Okay? Obviously, the ground state that gives this will be different anyway, right? We'll have to see how it's modified. Okay, so under these notations, I have now, let me write it here. I get an expression for the interaction, and now it is in a BCS approximation, so that's already a mean field result, and it's going to be, if you like, there is another constant here, plus, and that's, or let me write it like this, it's a minus, sum over k of delta C, let me just be careful with the notation, CK, C minus K dagger, plus its Hermitian conjugate, which is delta star C minus K CK. Okay? Okay, and now delta is a number, it's a parameter. This is a Hermitian Hamiltonian, completely legitimate in that sense, but it has a parameter that is allowed to be a complex number. Okay? Great. So we got, I'm going to take H naught plus V interaction in the BCS limit. I get something very simple, and in fact, it's a single body Hamiltonian, but the way it is written, the two terms together are not diagonal, because here I have C dagger C, or C dagger. Here I have C dagger, and C, right? So there are different types. But I can rewrite it very compactly in the following way. I'm going now to introduce a two-vector object. Yeah, you can take a picture. Okay. This I can erase now. Okay, so let me define the following object. I call it psi of k. And once again, it is an operator, an annihilation operator. And it has the following form. It's CK, C dagger of minus K. Okay? And it's like a spinor. Okay? Remember that what I called K and minus K are actually K vector. So I'm just writing this on the side. This is K up. And minus K, and minus K will be minus K. No? Okay. All right. This is called a Nambu spinor. So it's like a spinor with two components, but notice that it says one component is an annihilation, the other is a creation. Okay? What will be its Hermitian conjugate? So first of all, if this is a column vector, it's a row. It's a row, and it has C dagger K, C of minus K. Okay? And now I'm claiming that if you want to rewrite, you can rewrite the Hamiltonian, which up to a constant equals H naught plus V interaction BCS. You can write it in a compact way, and let's call this BCS Hamiltonian. You can write it in a matrix form, like this, where this is HK. It's a matrix, diagonal matrix. Diagonal in K space, sorry. Not diagonal, in fact it's not diagonal, but, and of course there is a summation of K. Okay, so it's, I'll just write it again. So HBCS is a sum over K of such terms. Okay? Where HK is a 2 by 2 matrix. And it has the following form. It's psi k minus psi delta delta star. Okay, and by just some algebra, actually, okay, to be more precise, there is a minus sign here because this is the way I define delta was without the minus sign that comes in the original attractive interaction. It's a matter of definition. This is it. That's the Hamiltonian. Okay, and we can, it's a 2 by 2 matrix, great. We can diagonalize it. For each K, we can diagonalize it, it's very convenient. And what is the result? So first of all, in order to diagonalize it, we have to apply some transformation on the psi's that will, some rotation transformation, okay? And once we do it, we get a diagonal form. But the eigenvalues of this matrix we can easily get. Okay, so let's solve for the eigenvalues first. Okay, so this I can erase, right? We're done with it. Okay, so first of all, there is some transformation, some unitary transformation. For each K, there is a unitary transformation that if I apply it on the psi K, I will, and I apply it on the left on the psi dagger, I will get a new Hamiltonian, okay? So now let me call the result of this transformation will give me some new operators that I want to denote with gamma instead of with C and C dagger. I have a gamma and gamma dagger. But they have the same indices. It has the same form as this, but if you rewrite them in terms of the C and C dagger, there's some superposition. Okay? Okay, and then these gammas diagonalize the Hamiltonian. Namely, uk minus 1 times hk times uk, okay, if I apply it on both sides, will give me a diagonal matrix, and it will have the following form. So let me first write it like this, okay? And we'll see what are this is diagonal. Now we want to find the eigenvalues. Okay, so for that we don't need to know the specifics of the transformation, because what do we have to do to diagonalize this matrix? To find the determinant of this minus lambda times I has to be 0, okay? So let me write down a formula for a general 2 by 2 matrix. Okay, this is going to be very useful. What do I want to erase? This I already did. Okay, so this is some exercise. I'm sure you have seen it. Okay, and here I have some, let me call it, I don't know, F and F star. So it's some Hermitian matrix, okay, 2 by 2. The eigenvalues of these are first there is an average of the two of the diagonal ones, plus minus the square root of epsilon 1 minus epsilon 2 square plus f square. Okay, you are familiar with this? I'm sure you have seen it. If not, please write it in a very, very prominent place in your notebook, because in the exam, surely, I don't know what will be the questions, but you surely will have to use it. That's like the level of diagonalizing matrices that we need for an exam. Okay, that's a general thing. Now, in the particular case, well, the matrix has the following form. It has epsilon 1 is minus epsilon 2, then the first term vanishes and you are only left with the square root. Okay? So the result of this will be ek and minus ek, where ek is the square root of psi square plus delta square. Okay. Right? Okay, so what did we get? So first of all, we see that, okay, that is a trick that you can always do, and it gave you new, so basically what I'm saying is that the Hamiltonian is no longer diagonal in the basis of the real electrons, okay? The electron operators, electron or hole, C and C dagger, are not good quantum numbers in a sense, or they are not the correct particles in which to describe this state, okay? In fact, what I'm going to get is that let me write now the diagonal form of the Hamiltonian more compactly in terms of the new operators gamma. Well, shall we, yeah, let me write it here. So the BCS Hamiltonian will have the form sum over k of ek gamma k dagger gamma k. This is how it looks. If I write it just as one term, okay. Actually, if you like, I can even bring back the spin here and write it as a sum over k vector and sigma, and the gamma with a sigma, but let's leave it like this, okay? So what does it describe? It looks like a new free Hamiltonian that has energies at Ek, and the Ek's are given by this expression. Now, remember, the original non-interacting Hamiltonian had energies psi that can be negative or positive because they are defined with respect to the Fermi energy. What can I say about the energies of these new particles? It's always positive, and not only that, it has a threshold, a finite threshold. It has an energy gap compared to zero. Okay, so what the way it looks is very simple. Okay, if this is k, okay, and somehow, okay, maybe that's not a good way to draw it. Let me parameterize it by psi of k, okay, which of course you can relate to k, but in a bit complicated way. So let's just plot it as a function of psi. And it has a minimum delta, absolute value, because delta is a complex number, but notice that the energy, which it must have real values, depends on its absolute value. So that's already an interesting result, because we don't exactly know what this delta represents, but we know that the energy of the state doesn't depend on the phase, only on the magnitude. What does it mean? That there is a lot of degeneracy. There are many states, actually any complex number that has magnitude delta, absolute value, will give us the same energy, okay? And this is how the spectrum looks like. If I plot it as a function of psi, it's kind of a hyperbola, symmetric, okay? And the most important feature is that it has a gap. Now a gap with respect to what? What did we define as our zero of energy? It's the Fermi level, okay? So if you like, the Fermi level, which is like the energy of our vacuum in the free electron gas case. And now, because of the attractive interaction, if all of that is true, namely if we can really get such a finite delta, then we created a new ground state, and the excitations, what these gas represents, are excitations above the new ground state, and they have a gap, okay? And the meaning of that is that as long as, for example, you cool the temperature below the scale that corresponds to this delta, you don't get excitations, okay? You basically get a ground state that is stable unless you somehow excite, there is a threshold to excite above it, okay? Okay, good. So what are these gammas? The gamma and gamma dagger describe creation and annihilation of something. Yeah? What's the question?
What is the y? C
No, that's energy. It's just a graph of, sorry, I forgot to write. It's EK. It's a graph of EK. Okay? Sorry about that. Okay? Yeah, so, right, so let's write what are the gammas. Actually, I can write it here. So I can let me write it explicitly. So gamma k. Let's make sure that mistakes. Yeah. So it's. So the gamma is a linear combination of C and C dagger, but not just C, not C and C dagger of the same K. It's C of K and C dagger of minus K. Okay. If you like, it's in terms of the original electrons, it's a superposition of electrons and holes, and its dagger with a minus K has the following form. So it's U minus K star C dagger minus K plus V C. Okay. Okay. All right. Now this is used. So you see that these coefficients must obey unitarity, right? It's a unitary transformation. Otherwise, the states. Why do they have to be unitary, by the way? I mean, what do I really want? I had some electrons. Electron operators obey some fermionic anti-commutators. And I want the new particles, by the way, they are called, this transformation is called Bogolyubov transformation. And the new particles that are annihilated and created are called Bogolyubov quasi-particles. So they are quasi-particles that are like electrons in the sense that they obey the same anti-commutators, okay? And if I want to preserve the anti-commutators, I must choose the coefficient U and V to obey that UK square plus VK square equals 1, okay?
Why it's plus in gamma dagger?
Okay, so, sorry, there's a good point. Okay, actually you're right, this is a minus, but the transformation, the symmetry of the transformation is such that if I put here, okay, let me do the following. So, this is just from the definition. I just took this
It's
one,
same,
and
same sign.
it's the same sign,
Okay.
but
Plus or minus is okay.
I can define it, so I can show that your k equals u minus k star, and vk equals minus v minus k star, okay? And
Why
then,
it's true?
actually,
It's definition or this algebra?
this is algebra, and in fact, if you want unitarity, you want it to be such that if you choose them, for example, to be real, they are just going to be cosine and sine of some angle. And then it's a rotation, it's just a rotation. And then it will be cosine theta minus sine and cosine theta plus, okay? So in fact, in the simplest version, of course they can be complex, but in the simplest version, if I choose them to be real, then you can parameterize them as a cosine of some angle, and then Vk is going to be sine of the same angle. Okay, and then obviously to base, cosine squared plus sine squared is 1. Okay, but more generally, at least when one of them you can always choose real, the other one may have a relative phase. Okay, if you want to be completely general up to global phase. All right? Yes?
Your psi, the number spinor, wasn't normalized. So why is it imported?
No, why wasn't it normalized? It's
you just added to
no, there are two components, but okay. I get your okay. I see where you're going. So what you would like to define something like this, right? I think this is what you mean. Okay, and if I write the anti-commutator of this the way I defined it, I get the C dagger k, C minus k times this, and then you see, then you get a factor of 2. I think this is what you meant. Okay, so if you wanted to normalize, put a factor of 1 over square root 2, but this factor will be trivial. It's just 1 over square root of the number of components. Okay, but the new spinor, gamma k, gamma, the new spinor will have the same factor of 1 over square root 2, but the gammas and the c's have to be, so the transformation has to be such that if C and C dagger obey the anti-commutators equal 1, then the gammas are the same. Okay? And for that reason, it has to be unitary. Okay? Good? Okay? All right. Okay, so far, what did I actually tell you? It looks like I'm playing a game that I still owe you a justification. What have I done? I assumed that there is some ground state for which some combination of operators has a finite expectation value. And I went along with this assumption, got a new Hamiltonian, I diagonalized it, and I get new particles, which I claim are describing the system, namely there's some ground state. It's going to play the role of my new vacuum, and above this ground state, I can excite particles, and they look like the spectrum has a gap. Okay, the spectrum of the gammas. And these particles are superpositions of electrons and holes in terms of the original electrons. Actually, I can also find expressions for the U and V. And notice that the angle theta, or the cosine and sine of theta, obviously are going to depend on delta, right? It's going to depend on delta because it's whatever transformation diagonalizes this matrix. Okay? So I'm not going to do the derivation. Sarah will do it in the next tutorial. I'm just mentioning that it is dependent on delta, and eventually, let's see, I'm not sure I'm going to get to this, so maybe I'll just give you motivation for what I'll do next week, is I owe you a justification that I'm allowed to play the game, because ultimately, okay, actually maybe let me do it this part now, and next week we'll have to continue, yeah?
לא סיימת לכתוב את מה שמחקת, כאילו זה...
לא, זה היה רק בתשובה לשאלה.
שזה גם ביותר.
לא, היא לא סיימה.
זה היה תשובה לשאלה, זה לא היה משהו שצריך לשמור, אוקיי? Okay, so let me erase this for the moment. So first of all, I am, yeah, okay. So let me remind you what I did. I assumed that there is an order parameter, which is this, that is non-zero. In fact, I named it phi k. And I assume that delta, I define delta to be V times the sum over k of this funny expectation value, okay? And then this delta appeared in my Hamiltonian, and I found that I can diagonalize my Hamiltonian by defining new particles that are like trivial free particles for the new Hamiltonian, okay? And in particular, in terms of the new particles, just write again what I erased. PCS can be written as up to a constant. It's just the sum over k, ek, gamma dagger k, gamma k. Okay, so it looks like free particles, but the energies are ek. Okay, and these particles, this gamma is defined as annihilation operator with respect to the ground state or the vacuum, the new vacuum that I define. And therefore this is a number operator, and if I look at expectation values of the gammas, the expectation values of the gammas are going to be, so gamma, this is now in the new ground state. This is going to be 0, okay, and the same for gamma dagger gamma. And gamma k prime. This is going to be what? The occupation of gamma, right? It's going to be actually a theta of, first of all, it will have a delta of k prime. and it's the number of particles, but it's actually given by the occupation. Okay, it's the occupation of these quasi-particles, but more explicitly, it's a theta of E Fermi minus the energy of this state. Okay? So it's going to be finite only if Ek is smaller than E Fermi. Okay? And yeah, and then right, and yeah, all right, and then gamma K dagger will be 1 minus that. Okay? So they just behave like regular particles, but the spectrum is different. It has a gap. Okay? But in any case, whatever it is, we can use this to compute the expectation value, right? So here, let me emphasize what I got here. This is a definition of delta, and it assumes that this is non-zero, and therefore delta is not zero. Okay? But this guy I can calculate independently because I already solved, I diagonalized the Hamiltonian, I found a transformation that diagonalizes the matrix, and I know the expectation values of the gammas in the new vacuum. I can convert the C's back to gammas and compute it explicitly just from the definition, and I will get something. This something will be a function of delta. Okay? You agree? Because I told you all the coefficients, the energies, everything depends on delta. Then what kind of equation will this become? It will be an equation of the form delta equals some function of delta. Now, maybe there's no solution except for the trivial. There is always a trivial solution. We know that because delta equals 0 just goes back to the free electron dust. But the question is whether there is a non-trivial solution. A non-trivial solution will have to satisfy a so-called gap equation because this delta is this gap in the spectrum, and it has to equal to a function of itself. It's a self-consistent equation. If we can prove that it has a finite solution, then we are in business because we found that there is such a state. We still may need to convince ourselves that it has lower energy. Otherwise, why would the system pick it up to be the ground state, right? So all this we'll do, I guess, next time because it's getting late and I'm also tired. But this is the idea, okay? It's important to understand the philosophy. So once again, because the game we play here is the same game you can play for other problems. Like you can look for, in this case we'll show that the new ground state that has all these nice properties is superconductive. It gives superconductivity. That part is actually the most difficult to explain within this level of theory, but it is a new state of matter that has a very funny property that it has a ground state that has a not well-defined number of particles, okay? And it has an order parameter that is complex, okay? Namely, there's not one ground state, there is a manifold of ground states, all the ground states with the same delta absolute value, but some phase, whatever is the phase, they're going to have the same energy, the same, everything the same, okay? So what does it mean? It means that if the system adapts this ground state, it chooses a phase spontaneously, okay? So the state is symmetric under rotation in arbitrary values of theta, but it chooses one theta and sticks to it, okay? What is it analogous to? It's like magnetism, ferromagnetism, right? You have a system of interacting spins, let's say, in some Heisenberg model, for example, and there's no external magnetic field, but you cool it down to low temperatures, and then it develops magnetism spontaneously. What does it mean? It means that the system spontaneously chooses to orient all the spins in one direction, out of the sphere, okay? Because there is spin rotation symmetry. It breaks the symmetry spontaneously and gives you an ordered state, okay? And this state, the ground state of BCS, is the same, but here it breaks the symmetry to rotation in an angle, one angle, not two, okay? But it's broken symmetry state, which characterizes by a choice of phase. It's like same as spin in the XY plane, if you think of it, okay? Okay, so I think this is enough for today, and next week we are going to derive this equation carefully and conclude with the topic.